Thanks everybody for joining. This is great to see such a very diverse audience here. I'm really happy to see everybody. So today we're going to be talking about Arctic cyclones. For those who are new to IARPIC, IARPIC is the Interagency Arctic Research Policy Committee, which brings together leaders from 18 agencies and departments and offices across the U.S. federal government to enhance collaboration on research in the Arctic. IARPIC Collaborations is the kind of the public branch of IARPIC, which aims to facilitate interagency communication, coordination, and collaboration to advance Arctic science. So the modeling collaboration team aims to enhance understanding of the integrated Arctic system through the use of regional and global Earth system models. So as I said, today we will be talking about modeling of Arctic cyclones. Arctic cyclones are a major cause of extreme events in the Arctic, but also have the ability to modify long-term climate due to their associated heat and moisture transports and their impact on the ocean and the sea ice. And a correct representation of these features in climate models is therefore critical for the accurate representation of future climate change. We'll have two speakers, and I'm very pleased to have both Elina and Xiangdong Zhang talk today. So we'll start with Elina. As she had a brief introduction of herself, she's a postdoctoral research fellow at Colorado State University, and she got a PhD from University of Colorado at Boulder, I think 2021. And she'll be talking about Arctic cyclones and sea ice interactions in the future climate. Elina,
thanks, Wilbert. All right. So does it look okay?
Looks perfect. Awesome.
All right.
Thank you.
Great. Thank you so much. I'm very happy to be here. And as Wilbert said, today we're going to be talking about sea ice and Arctic cyclone interactions in the future climate. So this is a work I did in my PhD studies at CU Boulder with John Casano, Elizabeth Casano, and Mark Seefeld. So the aim of my presentation today is to discuss the future relationships between Arctic cyclones and sea ice and how well the current models are representing these features and relationships and what we might expect in the future. And since we are looking into the future, we of course have to use climate models. So in this study, we used 6 CMAP6 models, ECR3, BCC, CSM2, MR, MRI, ESM2, 0, MIROC6, and the 2 MPI high-res and low-res models. All our data was 6 hourly because we wanted to kind of focus on the weather aspect, weather time scale kind of these climatology, and so that restricted our choice of models to these 6 models. And our horizontal resolution of all these models were between 100 kilometer and 250 kilometer. And I've listed here the roughness length over sea ice because this is something we will come back to in my talk later. Another kind of point I want to make is the metrics we used to define the intensity of these cyclones. So the tracking algorithm we used allowed us to get the area of the cyclone, which allowed us to calculate variables over the cyclone area. And this accumulated cyclone energy index is a metric that's commonly used in tropics to assess intensity of tropical cyclones. But the benefit of it is that it connects, it's based on the maximum wind speed of the cyclone over the cyclone area. So it relates the intensity of the cyclone with the kinetic energy of the cyclone. And since our focus was kind of on what's the interaction between the sea ice and the cyclone, you know, kind of looking into the impact and you know, what happens, and that's often you know, driven by the turbulent fluxes and by the wind speeds. We felt that this was a great addition to the metrics that are more commonly used, such as central percent of pressure of the cyclone or depth of the cyclone. So the ACE metric was calculated as a mean over the square wind speeds over the cyclone area. But we of course compare this metric also to the more traditional metrics to be kind of sure that it's reliable in the Arctic and also give us a better, like more comprehensive understanding of the cyclones. But this ACE index will, will go through multiple times in this talk. So moving on to the results, and when we talk about Arctic cyclones and how they interact with the sea ice, we often have multiple different variables that we can focus on, right? We can look at how many cyclones we have. We can look at how intense those cyclones are. When we're talking about intensity, we can pick multiple variables. And because the time is quite short today, I'll be only focusing on the cyclone intensity, and especially on this ACE accumulated cyclone energy index, because as I mentioned, it's kind of what gives us a lot of information about this interaction between the cyclone and the sea ice. When we have stronger sea winds, we can have larger changes in the sea ice and larger turbulent fluxes as a result. So kind of to get everybody started before we move on to the model results, let's take a quick look at reanalysis data to kind of get an idea what's happening now based on observations. Reanalysis, of course, are not completely observations, but because our observations in the Arctic, as I'm sure everybody knows, is very sparse, reanalysis data is kind of the best we have to go on. So here we have histograms of Arctic cyclone intensities, which are divided based on if the cyclone was located over open water, here in the left, loose sea ice in the middle, and concentrated sea ice on the right. So we have the percentage of time steps that the cyclone was located, what was the intensity of the cyclone based on the ACE metric. The green bars show ERA 5 data, blue bars CFSR, and yellow bars show ERA interim data. And the red bars or red lines show median values, and black lines show 90th percentile values. And this is for cold season and warm season. So as you can see, when cyclones were located over concentrated sea ice, which is sea ice over 85% sea ice concentration, our intensity of the cyclone was considerably higher than when we move to open water. So there appears to be this relationship between the intensity of the cyclone based on its kinetic energy and the sea ice concentration over which it stays. So this was kind of one of the main findings of a paper that we published last year. So this was a signal that was clearly shown in the reanalysis data. How well do CMAP6 models do? So first, right, when we talk about cyclones and sea ice, there's two components. So let's start with the sea ice. So here I'm showing the average sea ice concentration, seasonal sea ice concentration for these 6 CMAP6 models. ERA 5, which here is the solid black line, and then the multi-model average, which is the dashed black line. And this blue shading shows the 95th percentile interval, confidence interval, sorry. And here on the vertical axis, we have sea ice concentration, and on the horizontal axis, we have the years from which this study ran through, so 1985 to 2015. So this was from the CMAP6 historical runs. So as you can see that both in the cold and warm season, the models do pretty well with the average sea ice. What we were especially happy to see is that in the warm season, this strong decreasing trend that we have observed in the Arctic is also reproduced well with the CMAP6 models. One more point that I want to make on this is that this sea ice concentration was calculated over the cyclone area. So if you're trying to compare these to just like average sea ice concentration based on satellite data, for example, these plots won't be one-on-one because this will be emphasized by where the cyclones are located. But all right, so far so good. So, CMAP6, these 6 models seems to be doing pretty well with the sea ice. Well, what about cyclone intensity? Let's see when I can change that. So here I'm showing the ACE metric, and then dPdr, which can be thought as the approximate wind speed if we don't think of the friction in this case. But the dPdr is the pressure gradient over the cyclone area. And I'm showing the model differences. So you see 3PCC, the 2 MPI, low-res and high-res models, MRI and MIROC6 models, and the multimodal mean, their percentage differences to ERA5 for the ACE metric and dPdr. And as you can see, the ACE metrics is consistently underestimated by all the models. And this underestimation mostly seems to be due to the fact that the models underestimate the dPdr metric. And the underestimation of the dPdr was related to the fact that the models are a lot coarser resolution than the ERA5 model. However, when we look at, if we focus on certain models, for example, the MRI model, we can see that the models do well with the dPdr, so the wind speeds are, roughly correct, but we get actually an overestimation of the ACE metric. So we, wanted to see why this is, and as I mentioned, the roughness length of the models is something that actually we want to pay attention to. So the ACE metric, which was based on the wind speed, but it's also strongly affected by the surface. It's not just the, directly based on the dPdr. The surface roughness of the models also play a role. So here, ERA5 surface roughness varies between 0.001 and 0.006 meters based on, the wind speeds and the surface, whereas MRI has constantly lower only 0.001 roughness length, which is usually, an average would be lower than the ERA5. And since we have a lower surface roughness, we can get higher wind speeds even with the same pressure gradient force. This is also something to point about, that it's not just the surface roughness, also how these models predict the sea ice also plays in the role how the ACE is presented. But so it's kind of this combination of the dPdr, surface roughness, and where we have sea ice in these models that lead into these differences in the models. So the models are not doing exactly awesome when we talk about cyclone intensity with regard to ACE. So an ACE was the accumulated cyclone energy, which was related to the kinetic energy of the cyclone. So, but the models are the best we have. So what should we expect in the future? Let's again start with the sea ice. And again, this is kind of why I wanted to point out that this sea ice concentration is average over the cyclone areas. So this is a bit different than if you're just looking at a prediction of just sea ice concentration over the whole Arctic basin. But so this is from the future simulation SSP 585. And again, I'm showing the seasonal averages for the CMAP6 model and their multi-model average. And we can see that by 2100, we have very little sea ice left in the cold season, and in the warm season, the Arctic has already been practically ice-free for a while. So we have a really different situation in the Arctic that the cyclones will experience than what we have now. And this will definitely lead to differences in the cyclones. So here we have the cyclone lifetimes in the Arctic. The blue boxes show the historical run, and the red boxes show the SSP 585 run. The lines show the median values, and the green triangle shows the mean values. So as you can see, in both cold and the warm season, the cyclones will live longer in the future than they are currently living. And this makes sense, as we don't have as much ice in either season. We will have more moisture, more energy come into the Arctic. We will have less stability. We will have less surface roughness that would kind of slow down these cyclones. So, there's less things that would kind of make the cyclones disappear. All right, so we have cyclones that are living in the Arctic for longer. Do we see other changes in these cyclones? And we do. So here I'm showing the intensity metrics we used for these Arctic cyclones. So we have the ACE, accumulated cyclone energy, central pressure of the cyclone, so mean sea level pressure at the central point of the cyclone, depth of the cyclone, which is the difference between the central pressure and the edge pressure of the cyclone, and then the pressure gradient over the cyclone. And this I'm showing for the cold and warm season, the differences between the future, the average future strength minus the historical strength, historical intensity, the percentage difference between the future run and the historical run. And the bolded numbers show statistically significant differences. And as you can see, central pressure and ACE metric show stronger cyclones in the future. But what is interesting, especially interesting here, that when we see strong increase in the ACE metric, we don't see statistically significant difference in the DPDR. So this tells us that the change in the ACE is not really fueled by changing in the pressure gradient force. It is most likely related to changes in the surface. And that actually appears to be the reason. So here I am showing again, basically the same percentage difference as in the previous table, but shown spatially. So over these 250 times 250 grid boxes. So this is ECR3, BCC, MRI, MIROC6, and the two MPI models for cold and warm season, and the difference between the percentage difference between the future and the historical scenarios for the ACE metric. And the BCC and MIROC6 were the models that had very high surface roughness values, but they also showed strong decline in the sea ice. So we have a situation where in the historical scenario, in the current day, we have the sea ice slowing down the surface shrink strongly, but then when we have this sea ice melting, the wind speed will increase even with the same pressure force. To summarize, these models do not fully capture the local influence of sea ice decline in the Arctic. And I showed you one example of this with the cyclone intensities, which, the estimations by the models depend on multiple reasons. How models parameterize sea surface roughness, which affects the ACE calculation very much. By 2018, we can expect a summer ice-free Arctic, which leads to large changes in the Arctic climate, and also in, Arctic cyclones experience these changes strongly. Cyclone intensities are predicted to increase both by cyclone energy and central pressure, and this is due to the strong changes in the surface, which then leads large changes in cyclone energy. And last thing I want to kind of emphasize is that because we have this big change in the surface roughness and the surface of the cyclone, and it's something that we might not see in the kind of more traditional metrics such as depth or DPDR, it's very important when we are looking at future predictions of Arctic cyclones to use multiple metrics for cyclone intensity, so we get as comprehensive understanding of the future as possible. So that was me, after, I don't know if we have questions now or after Xiangdong's talk, but I'll be happy to answer any questions. Thank you.
Great, thanks, Elina. This was excellent presentation. Thank you.
Thank you.
Let's maybe do 4 or 5 minutes for questions. Then I'll hand it over to Xiangdong, and hopefully after that we'll have a little bit more time for discussion still. Are there any questions for Elina? And if you do, you can either put it in a chat or just speak up or raise your hand. Well, maybe I can start it off. I'm an oceanographer, so I'm totally ignorant about the atmosphere. But it's interesting that you see that the cyclone counts and intensity increases Is there any, how is this related to maybe a projected weakening of the meridional temperature gradient, basically, and the baroclinicity in the atmosphere? Can you comment on that?
Yes. So actually, what we found when we're doing this study is that when we have the decrease in the sea ice that's currently happening, that actually can cause increase in local cyclogenesis. So, cyclones in the Arctic, right, they can either form in the Arctic or they can come from mid-latitudes. And, as you mentioned, the decrease in the meridional pressure gradient, of course, can change the storm tracks in the mid-latitude, and we could have change in the cyclones coming in. But this kind of this interaction or this feature can be kind of over or like changed by the fact that we can have changes locally, where we can have more cyclones form locally, kind of regardless, in a sense, maybe not completely regardless, but somewhat regardless of the changes in the mid-latitudes. And then the question will, of course, be is kind of like which is stronger. And in recent years, it appears that this local cyclogenesis has been very strong, and we have gotten actually an increase of the cyclones in the Arctic. But then, of course, once we don't have any sea ice again, we don't have any, local baroclinicity in the Arctic. Stability of the Arctic will change, as I showed with the cyclone lifetime. So, in the future, we don't necessarily know exactly what will happen.
Great, thanks. Are there any other questions for Elina?
Hi, I have a question. Thank you. It's a very interesting talk. I'm very interested in the relations between the surface roughness and the intensity of the cyclone wind. So I wonder the reason why you choose that 6 simplified model. I feel like this model, 6 models, maybe not enough to establish the relations between the surface roughness and the simulated maximum wind of Arctic cyclone. So I wonder if you will check more model result of simplified models.
That is definitely a downside of this study, that we were only able to use 6 models. If there's more data available, it would definitely be interesting to look into more models. There's a couple of things that gives me more confident in these results. One is that we used 3 reanalysis products, and we saw this same relationship in these 3 reanalysis products also. So that kind of gives us not one-on-one comparable data sets, but that gives us at least a couple of more data sets. There's also been other studies that have looked at just wind speeds, and they have kind of shown similar results that we found with the Arctic cyclone energy, with that the surface roughness really affects kind of the changes in wind speed, and these predictions that in the future the wind speeds might be increasing. So I think I agree with you. Definitely using more models would be great, because 6 models isn't that many, but there are other incidental evidence that gives me more confidence in these results, and also kind of the physical relationship of that, what affects the wind speed, right? When we have ice versus open water, there's a large difference between the surface roughness.
Yeah, I agree. It can be expected that when the CS melting surface roughness is greatly reduced, the wind speed will be intensified. I agree. I understand this physicals. I just mean, I just mean when maybe there's for the simulated relationship in the simplified models for this surface roughness and wind speed, there may be other reasons. For example, the model physicals or model resolution. These factors may also, affect the simulated wind speed of Arctic cyclone. Yeah,
Yeah.
that's my, yeah.
That is definitely true. You know, having more models would be great.
Thank you.
Thank you.
All right. If you have more questions, then please put them in a chat, and I'm pretty sure Elina would be happy to answer them there as well. Xiangdong, second speaker, Xiangdong Zhang.
Okay, yeah.
Professor at the University of Alaska Fairbanks. He's got a 1992 PhD in atmospheric sciences from Nanjing University. And as he said in the introduction, he's got a wide range of expertise and interests, but specifically in Arctic climate change and variability and their impacts on mid-latitude extreme climate weather and hydrological events.
Can you see my slides well?
Yes, we can.
Okay, good. Yeah. Thank you guys for attending this webinar. So I'm going to talk. Elina gave a very good talk, so excellent. So very interesting link the model simulation to roughness. Yeah, later we can discuss more about that. Okay. Here I'm going to talk. My talk focus on process understanding. So process level understanding. So we did a case study by using high resolution wolf model. Because some audience may not be from atmosphere or may not be working on the Arctic cyclones. So I would like to give some introduction about the background. So extratropical cyclones is a classic topic. Is about 100 years, right? There's lots of publications about that, but most of them focus on the mid-latitude cyclones. For the Arctic, there are recent years, there are many new findings. There's also challenging questions. So recent years, there's a largely increased number of publications about Arctic cyclones, especially about its dynamics, its mechanisms, and its changes. So here I would like to introduce a number of motivations for our study. So when you look at the figure on the right, you can see the cyclone tracks. This shows the example of the cyclones. In year 5 is for year 2021, and also the cyclone tracks in DOE's new Earth system model E3SM with the Arctic regionally refined grid mesh. This figure shows a spin-up simulation in year 10. So when we look at those cyclone tracks, we can find the cyclones can be coming from Arctic cyclones can be from mid latitudes and also can be generated locally within Arctic. Like what Weber mentioned, the cyclones can cause the transient transport of heat and moisture into the Arctic, influence Arctic climate and weather. It also can cause an increase of turbulent flux, like momentum flux, sensible heat flux, and moisture flux across the interface between surface, for example, the ocean surface, CS surface, the land surface, and the atmosphere. That's the influence of heat flux, momentum flux exchange. In our previous study, we found that there are some interesting phenomena for the Arctic cyclones, like showing in the panel here. For example, the intensity of cyclones, Arctic cyclones, decrease during the summer. This is consistent with the mid-latitude cyclone systems. However, when we look at the cyclone count and the duration, so we found that there's an increase of cyclone count and the duration during the summer. This is a very unique feature for the Arctic. It's the opposite to the seasonal cycle of mid-latitude cyclones. So at the same time, we also found that there was increasing trend of cyclone activity over the Arctic. So we defined the Arctic cyclone index that include information from intensity and the duration or lifetime, and the number and the cyclone count. we integrate the 3 parameters together. We define this cyclone activity index. We found it was increased. And recently we extended this time series to the end of last year. So we found the intensification has been continued. That means there's a continuation of the intensification of the Arctic cyclone. So in addition to the cyclone itself, so cyclone can also have a large influence on Arctic Ocean sea ice and the temperature. So here shows the example we published last year. You can see the box plot shows the climatological sea ice, daily sea ice anomaly in August. In summer 2020 and 2016, there were 2 intense, super strong cyclones occurring over the Arctic. So at the same time, the sea ice anomaly, you can see the sea ice anomaly reached the low end of the climatological range. That means the Arctic cyclones can cause a large decrease of the sea ice. When we look at the day-to-day sea ice area changes, we also found the cyclone systems can accelerate the summer sea ice decrease. So at the same time, the cyclones, because there is a wind curl, right? The wind stress that can induce Ekman upwelling that transport deep layer warm water to the surface. That help to increase the oceanic heat flux to melt sea ice. So cyclones can also increase the ocean mixing. So when we look at the climatology or climate model simulations, so we also found that there is a larger uncertainties in the climate model simulation and the projections, like what Elina mentioned in her talk. So when we use our defined cyclone activity index and calculate this index for each model simulation, so for historical simulation, for historical run from 1950 to 2014, we can see there's a large spread of this chain of cyclone activity index. That means the model cannot get consistent results about the changes of the cyclone for the present day for history. So this will be very challenging for future projection of a cyclone activity index, of cyclone activity in changes. So the question is, so what's the driving mechanism for the changes of the cyclone, for shaping the intensification of the cyclone system over the Arctic? So to answer these scientific questions, we use a WRF model, high resolution WRF model, to do modeling study on selected intense cyclone system over the Arctic. We worked on the 3 selected cyclone systems during the summer. One is in September 2010, other one is in October 2012. The third one is in October 2016. So all those 3 cyclone systems are very famous, draw a lot of attention in the community. So the WRF model we use has a resolution of 10 kilometers. We, throughout many years, we physically optimize this WRF model for its application to the Arctic, so that it can produce the best performance over the Arctic. So for example, we use this WRF model simulation to develop a high resolution reanalysis data for Pacific Arctic Ocean. So the Taylor diagram shows a comparison of our reanalysis data with all other global and regional reanalysis data. So our reanalysis data is called C-bar. So you can see the C-bar shows a much better performance compared with the other reanalysis products. For the cyclone simulations, we also did comparison of model simulation results with the field observation. So the right panel shows the model simulated temperature, humidity, and the wind speed. And it's a comparison with the GPS radio sound data on the icebreaker over the Arctic. So we can see the model capture the observations very well. So this gives us confidence to trust this model to do model study on the cyclone physical mechanisms. Yeah. So next slide shows the simulation for the 2010 case. So because there are many details, considering the limited time, I'm not going to discuss of the detailed information. So here I would like to mention the cyclone system has distinct features from conventional baroclinic driven mid-latitude cyclones. For example, when we look at this row of the figure, we can see the cyclone centers at a different level is stacked. It's vertically stacked. It's become a barotropic structure. When this cyclone became a barotropic structure, it still can stay over the Arctic for a very long time, for several days. This is quite different from mid-latitude cyclones. This actually is really challenging. So when we submit a paper for publication a few years ago, so some colleagues strongly have a different opinion. So they simply believe the Arctic cyclone is the same as mid-latitude cyclones, but we found that they are different. So we spent much time to persuade, to convince the reviewers and got paper published. You know, right now the topic becomes a hot topic. The ONR found a large number of projects are working on this. Okay, so other feature from this simulation results we can find is in the troposphere, there are cold temperature core, but in the low stratosphere, there's a warm core. So this is very interesting. This also determines why the stratosphere, low stratosphere, or some people, some colleagues call it the tropopause vortex play a role in the Arctic cyclone intensification and persistency. So this is the case for 2021 cyclone. So we also did other, like what I mentioned, we also did other modern study. So on 2016 cyclone, intense cyclone over the Arctic, we basically found the same feature, same dynamic structure. So when cyclone, okay, there was previously, there was a cyclone in the center of the Arctic, but in our study, we focused on this newly born cyclone from the Barents Sea. And this cyclone developed, intensified, and propagate eastward along the Eurasia coast area to the Central Arctic. You can see from here. And then to the Central Arctic, it's become stronger and cover the entire Central Arctic. So when we look at the cyclone structures at a different level, we also found, okay, it shows basically the barotropic structure from the surface up to the low stratosphere, right? The last panel shows, last column shows a tropopause pressure and the tropopause. You can see the tropopause vortex or low stratosphere vortex also coupled become a move about to the surface cyclone and coupled with the troposphere and the surface cyclone system. So this cyclone system also shows a cold core in troposphere and a warm core in the up level in low stratosphere. So this is very, very, the structure basically consistent across the different cyclones we selected, we studied. Yeah, because we only made a decision to give this presentation a week ago, so I did not catch time to include more simulation results from 2016 case. So I mainly use the results from 2010 case to show our findings and the dynamic the ideas, or I can say the ideas we proposed. Okay. So let's look at when we talk about the cyclone system, it has a different structure. It's persistent for a long time. It got intensified. It's a strong cyclones. So what's the reason for that? So we look at the different contributing factors. The first one, we look at the baroclinic instability. So we calculate the maximum ED growth rate. So it's defined by this formula. So we can see there's a larger value of ED growth rate occur at the beginning, first part of the cyclones, is the cyclone development. This is the time, September 24 to 30. So you can see the larger value of ED growth rate mainly stay in the low level of troposphere and during the first state of the cyclone development. This means this suggests the baroclinic instability mainly support the generation of the cyclones and the intensification of the cyclones for the first phase. When we look at the surface heat flux, we also can see this is the turbulent heat flux from the ocean and the sea ice to the atmosphere. We also can see there's a larger increase of turbulent heat flux in the first phase, and then the turbulent heat flux decreases with the time. So you can see it's getting smaller as the second half of the cyclone lifetime. So this tells us the baroclinic instability and the turbulent heat flux may not play a role in the second half of the lifetime of cyclone system, cyclone development. So we have to think about the different physical mechanism, right? And then we calculate the PV potential vorticity. Okay, it's quite interesting. We found that there is a PV anomaly in the upper level, in the low troposphere, stratosphere, and the tropopause. So we can see there is a PV anomaly. Because of the PV anomaly, that's caused a synoptic scale, the jet stream. There's a red color shows the wind speed. So there's a jet surrounding this PV anomaly. So the question is,
Zhang,
okay.
Sorry, I hate to do this, but we're coming close to time, so I'll let everyone know.
Yeah, I go through quickly. Yeah.
Okay, that'll be great, and we can keep the Zoom open a few minutes late if folks are able to stay on. But yeah, thank you very much.
Okay, sure. So the thing is the PV anomaly play important role. This is time of evolution of the PV anomaly. We can see the PV anomaly stay over there over the time, right? So this suggests the downward intrusion of low stratosphere and the tropopause vortex play important role in intensification of the cyclone system and the maintenance of the cyclone system. Yeah, this is major results. And then we look at, we also did a thermodynamic analysis to look at what causes PV anomaly. So our finding is the vertical motion induced adiabatic heating is very important to maintain this PV anomaly, sustaining the cyclone system over the Arctic. Yeah, I'm going to skip the sensitivity experiments. So, and then this is a summary of this study and the concept model. So the intense Arctic cyclone study here shows the different dynamic structures from mid-latitude cyclones. This is very important. The second one is the baroclinic instability mainly occur as for the first phase of cyclone development. Throughout the entire cyclone development, the downward intrusion of low stratosphere and the tropopause vortex play very important role. Yeah. Okay, I finish here. It's a simple summary. If you have questions, just send me email or.
Great, and thanks, Xiangdong. Yeah, we're getting close to the top of the hour, as Hazel said. She will have some time to leave the Zoom room open. So let's get some discussion started. But for those who have to sign off at the top of the hour or before that, And thanks so much for joining, and really appreciate your participation today. And we don't have a next session scheduled for the modeling team, but we're looking at several different options. So keep your eyes posted. We'll keep you posted on that. And if you have any ideas for topics that you would like to see addressed by the modeling team, then please let us know. So thank you. So are there any questions for Xiangdong?
Mm-hmm. Oh, why I cannot see my, oh, wait, okay, next slide here.
Hi, it's a great talk. It's very extraordinary work. I very like it. It's very interesting. Yeah. I did read your paper carefully, but I have a quick question. Have you looked at the winter cyclone, Arctic cyclone? Do you think the stratosphere polar vortex also play a important role in the winter Arctic cyclone?
Yes, we actually, when my student when he worked with me, we look at the cyclones during 4 seasons. The physical mechanism can be different. Actually, this is a challenging question. That's when we prepare this study and submit paper, why there's some colleagues mentioned, okay, so we don't think there is polar vortex in summer. This is correct. During the summertime, so there is no planetary polar vortex. So that's the reason during the winter time, the influence of a polar vortex on the surface cyclone is quite different from the summer. So this is the reason here for the summer I use a low stratosphere vortex. I did not use a common name, planetary polar vortex. So they are completely different concepts. Yeah. During the winter time, because the planetary stratosphere polar vortex is very strong. That's from the traditional dynamics. Actually, the Hoskins published paper several decades ago, right? That can steer the cyclone development from the mid-latitude up to the subarctic. Yeah. So within Arctic, I think it's still open question. Yeah, because I don't think the long waves can generally cross the center of the cyclone of the Arctic region. Yeah.
Okay, thank you. It's very interesting.
All right, Steve?
Hi, thanks. That was a very fascinating talk. So in terms of the differences with the mid-latitude cyclones, I was wondering, so in mid-latitude cyclones, you still have the PV anomaly directly over the surface cyclone, but they weaken. And in the Arctic, you're saying that's happening as well, but it's not weakening. Do you know, can you maybe elaborate on what the physical mechanism difference is between those cases?
Yeah, that's a very good question. Yeah, so when we look at the mid-latitude the PV anomalies. So generally we talk about like what I mentioned, associated with the planetary polar vortex and the jet stream. So that can be reflected as the planetary trough, right? So in that case, there's still vertically tilted structure. So the PV anomaly or planetary stratosphere vortex can enhance baroclinic structure. That's a play role. That's a help intensification of the surface cyclone system. So the scale is big, and also the process is different. That is through enhanced baroclinicity. But over the Arctic for the summer, because the cyclone, the PV anomaly as a synoptical scale or mesoscale is mainly through enhanced the mesoscale the jet stream or like the vortex at the upper level, and that stir up the troposphere and the surface cyclone system. Yeah, the dynamics can be different. Yeah.
Thank you.
Okay, thank you.
All right, great. Any more questions? Well, if not, then maybe we should wrap it up. I'm pretty sure if you have questions, then please reach out to Xiangdong or Elina. Also, their presentations have been posted on the IARPIC website, the event page for this one. So if you want to ever get back and take a look at what they presented, then that's where you can find the slides. Hazel, is there anything else that you want to say in conclusion?
Nope, just echoing your thanks. And yeah, again, the meeting recording and notes will be posted shortly. So really appreciate you all joining us today, and I hope you have a wonderful rest of your day and week.
Thanks,
Okay,
everybody.
thank you.
Thank you. Bye.